So I think we've developed all the tools that we need now to talk about the total Lagrangian formulation in 3D. We've developed the continuum measures that we need to talk about, both in terms of stress and strain. We've developed the equations in 1D, and what we're going to do here is we're just going to extend by parallel the equations from 1D to 3D. Although we could derive them in a similar fashion, right? We could take the momentum equation. We could create the weak form, we could discretize the weak form, but we're going to see that it gives us essentially the same form as what we developed for 1D, so I can leave that as an exercise. So we'll begin by recalling our finite element discretized momentum equation from the 1D total Lagrangian formulation. And if you remember, that looked like we had a mass matrix, call it M, times our acceleration, U double dot, is equal to our external force vector minus our internal force vector for giving us a net force vector, call it F. Okay? We'll call this equation 1. In 3D, we're going to have a similar discretization, but with terms defined in 3D. Okay, so let's just review. We'll write down the 1D and then we'll write the 3D, the corresponding 3D. Okay, so let's first talk about the measure of stress. Okay, so in 1D, what did we have? So we had we used a nominal stress. So we basically said that F is equal to P times A naught, or if we wanted to write in differential form, we could say that DF is equal to P dA naught. Right? Call that equation 2. And what does it look like in 3D? Well, the nominal stress, as we've defined it in 1D, becomes the same, the nominal stress, or depending on your definition, the first Peel-Kirchhoff stress in 3D. We're going to go ahead and use the nominal stress P such that, and I'm going to write down what I had written when we talked about stress measures earlier, N naught times P d gamma naught, right, where that's the unit of surface area, or differential surface area, is equal to T naught times d gamma naught, right? Remember, T naught is a pseudo traction. That's this term is equal to the true traction times the area in the current coordinates, but regardless, that is equal to the vector dF. Okay, let's call that equation 3. How about our measure of strain? Okay, in 1D, right, we had that we defined it as epsilon is equal to F, which was the deformation gradient, x as a function of time minus 1. Call that equation 4. Okay, we have a similar equation in 3D, but we're going to go ahead and use the green Lagrange, or the Lagrange strain tensor. Okay, and we can write that as E, right, is equal to 1/2 F transpose times F, right? These are tensors, minus I, the identity tensor, right? That's how we define that. If we wanted to write that in index notation, that would just look like Eij is equal to 1/2 F Ki F Kj minus delta Ij, right? We'll collectively call these equations 5. And I just should define what is F. F is the deformation gradient tensor. Okay? So we had the M term. What's that mass matrix look like? In 1D, we wrote it as the mass matrix M is equal to integral from x1 to x2 times n transpose times rho naught a naught dx, right? Call that equation 6. And in 3D, okay, we are going to write something similar I'm going to write this now in index notation instead of matrix notation just because it's more convenient and compact to write it this way. I'm going to say Mij, capital J, is equal to, is delta Ij, and it'll become clear what this means in a second, times the integral over omega naught, which is the area of, or the volume rather, of the element in its reference coordinates, of the quantity, let's see, Ni, which I'll remind you is a function of x, Nj, which is also a function of x, times rho naught d omega naught, right? So very, very similar. Call that equation 7. So what is this term here? If you just remove the delta Ij in front of it, it's exactly the same term as equation 6. So really we basically have a 3 by 3 mass matrix for each of the 3 directions Ij. Okay. And I'll also, since I kind of introduced this weird notation, I'll just say little I and little j. Those correspond to the xy, xyz directions. So 1, 2, and 3, right? And then capital I, capital J, corresponds to the nodes of the element. Okay, so I and j have a different number of components than little I, little j, right? Which just go from 1 to 3. In a 8-node brick, capital I and capital J will go from 1 to 8, right? So one thing we didn't really need to worry about too much in the 1D case was the mapping to natural coordinates, although we could have. But in the 3D case, we do. We still need to work that. So let me just write what that looks like. So accounting for the mapping to natural coordinates, we would write that Mij, capital J, is equal to delta Ij. And now we'll take the integral over the natural coordinates, which I'll just denote as a square here. Rho naught, still Ni, although we're going to have to use our mapping between x and c as our natural coordinates. Nj, and then I'm going to say j c naught, right? And then d over that natural coordinate element. So this is the Jacobian, not of the transform, not of the current to reference state, but from the reference state to the natural coordinates. Okay. So I want to mention that as I move through here. Whenever I write C for this particular lecture, I'm not referring to the current coordinates. I'm referring to the natural coordinates. Okay. So let me just say Jacobian of the transformation from the reference to the natural. Okay? Okay, how about internal forces? So what did we have? In 1D, I'll just remind you of this. You can go back to the lecture on it. We had that the internal force vector was equal to the integral from x1 to x2 of the quantity n partial with respect to capital X, right, the reference coordinate, times a naught times the nominal stress P dx, right? Let's call this equation 9. And in 3D, we basically have a similar formulation. So in 3D, we're going to, again, not use the vector form. We're going to write it in this kind of hybrid form. So this will be F internal little I, capital I. And now this is going to be equal to the integral over omega naught, as you would expect, times the quantity B, capital I, little j, and I'm going to put a superscript naught, transpose, times the quantity P, ji, d omega naught, right? Call that equation 10. And we could also, if I want to write out what B is, it looks just like what we had up above. This is the integral of over omega naught. Bi is going to be the partial of n cap I, right, which is a function of x, with respect to x little j, p ji d omega naught. But remember that there's going to have to be a transformation, because while this looks convenient, we don't actually define our interpolation functions in terms of capital X. We define it in terms of natural coordinates xi, eta, and zeta, right? So let's collectively call these equations 10. Okay, how about external forces? In 1D, our external force vector looked like the integral from x1 to x2 times our interpolation function vector n times rho naught a naught b dx plus n, that vector, times a naught times p evaluated on the boundary where traction is applied. Okay, let's call that equation 11. Okay, the parallel in 3D is f, a similar form now, little I, capital I, external, is going to be equal to, this integral now becomes over omega naught. Now this becomes ni times rho naught, and then we have a bi, little I here now, right? And then this a naught dx becomes d omega naught. And then over here, instead of just being basically a 2-point evaluation, we're going to have to integrate over the boundary. So we're going to go ahead and integrate now over the boundary where the traction is applied. And this becomes ni ti bar naught times d omega naught, right? Remember, this is that pseudo force term, or pseudo traction. So if you actually have to compute that, you're going to have to go back and do some transformations to compute that value. We'll call this equation 12. Okay? So I think the external forces and how we apply those is fairly straightforward. We do it in the same way that we did with the 1D case. The internal forces are a little bit complex to calculate, not the least of which is because we so rarely use something like the nominal stress tensor P to define any sort of constitutive law. So let me just go through with you this 8-step process for computing the internal nodal force quantity there. Okay, so to compute the internal nodal forces, the first thing that we do is we're going to initialize the internal force quantity to 0. Okay, and I should say that this is at the element level, right? So this is assuming this is over an element that we're working. The assembly proceeds as we've done before. Let me also, I don't want to call this I, let's call this 1. Okay, step 2 is we're going to basically loop over all integration points. So for all integration points, and we'll call those C sub Q, right? This is sort of like a little piece of pseudocode that you could ultimately translate into a piece of working code. This is where we have our sort of 8-step procedure. The first thing that we're going to do is compute that derivative component. So compute b capital I little j naught, which we said was equal to partial of ni evaluated at cq, right? Partial xj for all I, right? We have to go through each point, integration point, right? For if there's I nodes, there are presumably there are I integration points in this fully integrated element. Okay, number 2. We're going to define this term H ij that we'll call b ij naught times u I little I capital I, okay? And what we're going to do is we're going to use this H term to compute our deformation gradient tensor, okay? And you can go back through the derivation of this if you want, but I'm mostly just giving you the recipe here. This is just Fij then will be equal to delta Ij plus Hij, right? So, and then similarly, we could say that J, that Jacobian that we need for a lot of our transformations, is equal to the determinant of Fij. Okay? Again, these will be evaluated at xc q. Okay? Number 4. Once we have these definitions, we can go ahead and compute our strain. So we can say that EIJ is equal to 1/2. Right, H basically is a displacement gradient term, and we've written the Green's strain tensor in terms of displacement gradients as Hij plus Hji plus Hik Hkj, right? So we can compute that. Okay, if we need to compute some other quantities, which we may well need, we can compute any of the sort of derivative quantities from that. So we could compute the strain rate term if we wanted. We would compute that as delta E, which we just computed, right? And hopefully we have the previous E over delta T, right? We could compute F dot, right? The deformation gradient rate, which would just be equal to delta F divided by delta T. And if we needed to, we could compute our rate of deformation D, which we said before was just a symmetric part of F dot times F inverse, right? So you can compute any of those quantities, and then now that you have whatever, hopefully the relevant measure of deformation that you need, now we can go ahead and compute the stress. So we can typically we'll compute the PK2 stress, which we denote as S, or we could compute the Cauchy stress, which we denote as sigma, from whatever constitutive equation that we want, from the chosen constitutive equation. Okay, and then once we have that, we can't just use the either S or sigma. We have to convert that back now to P, right? So convert the stress, convert S or sigma to P, right? Using the equations either that P is equal to S times F transpose, or that P is equal to J times F inverse times sigma. Okay? So either of those. So now that we get P, now we can go back and make our substitution. So, but one more step in this sort of for loop. Okay, so number 8. Okay, we're gonna update F int little I cap I. We're gonna update it by the summation of whatever the previous value of it was, plus the quantity B capital I little j naught transpose times P Ji that we just computed above, times the quantity Jc naught, right, times now WQ bar. And what is WQ bar? That's our quadrature weight. Okay, and we do this for all I, right? Okay, I'm going to make a note here that in step 1, it requires us computing this quantity del Ni del Xj, which we know via the chain rule we could write as del Ni del Ck del Ck del Xj, right? Let's call that equation 13. And this quantity we can get because this is the kind of, we can look up n with respect to our natural coordinates, because that's how it's typically defined, right? So I'll just say that since we are typically given, that x is some function of xi, eta, and zeta, or in this case we're going to just call these xi1, xi2, and xi3, right? Those are our x, y, and z natural coordinates. Okay, because of that, we define the quantity j xi naught, I'm going to put this as a matrix now, is equal to the partial of xi with respect to Cj, right? So that if we wanted to take Jc naught inverse, that would look like a delta, or the partial rather, of, and I'm going to put it in a form I can make my substitution in, Ck over Xj. Okay? So I can go ahead and use this definition to rewrite equation 13. So we can rewrite 13 as partial of n cap I partial x little j is equal to partial of n cap I partial of Ck, which you can calculate just by knowing the interpolation functions, because by looking them up, and then times this transformation matrix J naught inverse, right? Which I can just say has units Kj, right? Or has indices Kj. Okay, let's call that equation 14. So that's how you would do that. And I'll just remind you again that in the development here, so again, another note. I'll just say here we've used Xi as the natural coordinate, not as the current coordinate as we have in the past. Okay? So that really is all there is to the total Lagrangian formulation. That's how we would evaluate the vectors, or the quantities rather, and that's the methodology. We would basically employ the same methodology to solve it, exactly the same methodology as we did, as we talked about already with the 1D case. In at least the dynamic case, we could use an explicit form or something like that.